Hello, everyone. Hello, everyone, and welcome to Tesla Unwired. Thank you for joining us for another fascinating interactive episode. We have today Greg Leyh, an electrical engineer and builder of some of the world's largest Tesla coils. Greg will also share a video presentation with us, which is super exciting. He's going to discuss Tesla's wireless power concept and how large Tesla towers could unlock the secrets of natural lighting. We also have with us today Executive Director of the Tesla Science Center, Marc Alessi. I just want to make a quick announcement to remind everyone to please shut off your video, be sure to mute yourselves, and to remind you that we will be taking questions and answers at the end of this segment. You'll find at the bottom of your screen a chat section. Please enter all of your questions down there, and we'll be sure to get to as many as we can at the end of the segment. Right now, I'd like to introduce Marc Alessi, our Executive Director. Marc?
Thank you, Lisa, and thank you, Greg, for joining us. I want to thank our audience. Happy to see this week we are able to accommodate more audience members than we were for the first webcast. We were planning on launching this webcast a few months from now, but because we're all at home social distancing, we thought it was an opportune time to move this programming up. And we started this webcast with Mark Seifer, a biographer of Tesla. It was a very successful program. And now I'm happy to welcome our current guest, Greg Leyh. Before I do, I'd like to acknowledge some of our Tesla VIPs in the audience today, and I hope we hear from each of you later on during the question and answer period. But first, I'd like to recognize Nick Lanshaw, who's joined this web call. Nick is the president and founder of the Tesla Science Foundation. He's located down in Philadelphia and has been a tremendous supporter and advisor for us here at the Tesla Science Center. Likewise, Richard Matthias, who builds Tesla coils himself and has been a very generous benefactor to the Tesla Science Center by donating one of his foundation's coils that will be prominently displayed at the Tesla Science Center once we open our facilities, and may be available for some of the other exhibits that we'll be putting on. And, you know, I met Greg Leyh a little over a year ago. The Tesla Science Center put on its first exhibit on the West Coast. We had a benefactor, Warren Dewey, who opened up his loft and donated it to us for a number of months. Warren felt that we should introduce this project to the Silicon Valley. Well, we had a lot of supporters out of the West Coast and the Silicon Valley from our crowdfund. So we saw that as an opportunity to continue to engage our crowd and go to where our crowd is. And it was a very successful exhibit, partly because of Greg's involvement. So as we were trying to pull that exhibit together and showcase what would make this project special, we were introduced to Greg by some of the staff at the Exploratorium in San Francisco. They said that he was a go-to person when you're dealing with anything over 5,000 volts. What we found, you know, they told us he worked at Google X and was an expert on everything over 5,000 volts. But what we found was someone that built the largest Tesla coils in the world and actually studies lightning and runs Lightning on Demand, LOD.org, which I think you see on your screen now. Greg had brought some of his coils to the exhibit, and at the end of each event, people would file out of the loft into the parking lot, and Greg would fire off a 20-foot coil, and it was definitely the highlight of each event. After that, Greg stayed engaged with us, has advised us a great deal on some of the science around Tesla's inventions, and personally drove the largest Tesla coil in the world from California to New York to showcase it during Tesla's birthday this past July. It ended up being the most successful event we ever ran on site. The birthday party always increased by about 100 to 150 people every year. And prior to this event, we were at about 700 or 800 guests at the Tesla birthday party. But when we were able to announce that Greg was bringing this coil, that helped bring the crowd up to about 1,400 people, which is the most we've ever had on site. So Greg, thank you for all that you do with us. I think the crowd has already known your name and seen what you've been doing, but I think we'd like to know a little bit about what the typical day is for you between your day job at Google X and then your research into Lightning with Lightning on Demand. Can you give us a little bit of insight into that?
Sure. Well, my typical day job, I work with a group called Climate and Energy, and it's our job to try to figure out ways to reduce carbon footprints and sequester carbon, and all around just try to figure out ways to help the climate become, or our presence in the climate to become more sustainable. Aside from that, my real job is Lightning on Demand, where I'm trying to figure out how to essentially replicate the what's called the creation point in a storm cloud where lightning starts. It's odd to think that how that works right now is presently unknown. We know how lightning propagates once it starts, but not how it actually begins. And I think there's a way to replicate that here on the ground and figure out in detail how that works.
That's great. You know, when you mention you know, some of the day job in terms of protecting the environment or reducing our footprint, I think that is along the lines of how Nikola Tesla used to view the world in general. I have always found it remarkable, and it makes me very proud to work with the Tesla Science Center when I think of our namesake, Nikola Tesla, at the door of the Industrial Revolution, making such enormous progress through his inventions, enabling alternating current electricity. But what he saw was the ability to take hydropower from places like Niagara Falls, which he unlocked the power of Niagara Falls, and he wanted to produce clean energy. He looked at coal-fired power plants at that time and said, this is not the direction we should be going, that we can harness the energy that is natural to the earth, whether it's the sun, whether it's the wind, whether it's hydro, and that would be a better future for us. So the fact that I view you as a Tesla of today, and that's the kind of research that you're doing, you know, during the day, that's great. But tell me a little bit more about your research into Lightning. How did you get involved with that?
Well, I'm an electrical engineer by trade, and a while back when I was reading about the physics of lightning by Uman, who's a professor at the University of Florida, it kind of struck me as odd that there wasn't a good description of how lightning starts in clouds, especially given that the electric fields inside storm clouds are only about 1/20 of what you need to normally break down air and produce a discharge. And that seemed really odd and interesting too, because that means storm clouds have some kind of trick that they use to get around this fundamental limit. And there's a lot of theories now on how that trick works, but we still don't know. And I think there's an empirical way to find out how it works. And that's been the focus of my work to date, is to come to that empirical solution to the problem.
That's great. So I see that you have a slide up here. I think, you know, I can reserve some of my questions. I'd like to see a little bit more. I've seen part of this presentation, and I'll tell our audience, at one of our VIP events out in Oakland, we started hosting events for Tesla Motor employees that had caught wind that we had this event out on the West Coast. They saw that there would be an interest among some of their employees. We agreed to have a VIP Tesla Motor night. We thought there was a lot of great synergy there, the Tesla Science Center and Tesla Motor employees at the Tesla exhibit. It sold out within the first 5 minutes of posting it. So we agreed to do a second event. That sold out within 5 minutes of posting it. So we agreed to do a third event. So we did a series of events. And then eventually we said, we'll come out there for a much larger event down the road. But at one of the final events that we did with Tesla Motor employees, Greg had given a presentation on his research. And I think that's pretty much what you're going to see, a rendition of that now. I could be wrong, but Greg, can you please take it away from here?
Okay, well, thanks for coming out and tuning in today, everyone. As I mentioned, and you probably surmised, the study of large-scale electrical physics is an active hobby of mine. It's kind of a hobby that's gotten away from me recently. It's endlessly fascinating and surprisingly unexplored. I started this work way back when 3-letter URLs were free for the taking. So visit the website here at LOD.org if you'd like to find out more details about the scientific motivations behind the project. I imagine everybody here is familiar with Nikola Tesla, and that his most famous invention was the AC induction motor. He built single-phase and eventually polyphase versions of this. I think right now there's about 13 billion horsepower of induction motors in service. And one of the largest ones would be there's a 60,000 horsepower motor that's used in the 80 by 120 wind tunnel at NASA. And although the AC induction motor was his most famous invention, he spent a great deal of his life working on his system to send power around the world without wires. Tesla's idea was to place a number of high voltage towers, like these ones in the diagram, at strategic locations around the globe. Each tower would then capacitively couple energy up to the upper atmosphere, which Tesla believed to be reasonably conductive based on his work with rarefied gases in tubes at the time. It's also interesting that Tesla developed this scheme several decades before the ionosphere was discovered. No doubt Tesla would have been overjoyed to learn that there was already a pre-ionized conductive layer up there. In 1899, Tesla started working on the drive system for his towers at Colorado Springs. This picture is his lab there at Colorado Springs. And this fence that goes around the outside here is actually the coil form for the primary and secondary. The secondary fed this coil in the center, which is called the tertiary coil. And that was connected to a raised aerial that went through the roof, some 50 or 60 feet, which Tesla used to measure coupling to the upper atmosphere. After finishing the drive system in Colorado Springs, he started building a 187-foot tall tower back in Long Island at Wardenclyffe. This tower is made completely out of wood. And there's a concrete and granite foundation at the bottom. And the structure was designed redundantly. That is, any one of the structural members could be removed and replaced without sacrificing the integrity of the tower. Up here on top of the tower is a large spheroidal shape called the top electrode. And it has a radius of curvature that's sufficient to hold probably 10 to 20 million volts without arcing out. And Tesla believed that the fields emanating from this structure would radiate upwards and couple power towards the sky. Unfortunately, Tesla ran out of money halfway through the project, so he never got to finish it and close the switch. Ultimately, Wardenclyffe was torn down and scrapped in 1915 to satisfy Tesla's creditors. So would it have worked? There's plenty of arguments on both sides, even today. Personally, I was a skeptic. After all, radio transmitters today are far more powerful than Wardenclyffe, yet they only deliver a fraction of a microwatt to receiver antennas. So how could Wardenclyffe have possibly delivered kilowatts? But then one day I witnessed a bizarre electrical accident. I actually caused this accident by leaving this poor clip lead connected across the terminals of a coil in my shop. But what's interesting here is that when the coil burned this clip lead, the coil itself was actually disconnected from everything and stored away in the corner of the lab at the time. At the time, I was running a similar coil across the room when somebody with me there started yelling about smoke. After we went over and found the smoldering clip lead hanging from the disconnected coil, I just stared at it for a few moments and wondered, what in the hell just happened here? So of course, the first thing we tried to do was to recreate the accident. We pulled out the stored coil and set it up as a receiver here. I don't know if you can see my cursor. And then we set up this first coil as the transmitter. And this time, instead of a clip lead, we gave the receiver coil 800 watts worth of light bulbs as a test load. Now I thought 800 watts of bulbs would be more than enough, but the receiving coil was able to drive them way beyond 800 watts if we moved the transmitting coil any closer than 5 meters. Now this made no sense to me at all, since the electric coupling between these two coils is incredibly weak. It measured at only 10 femtofarads, which is 1/100th of a millionth of a farad. But later I ran some detailed circuit simulations, which confirmed that even this amazingly small amount of coupling can pass dangerous amounts of power between two well-tuned Tesla coils, all through the magic of resonance. After this discovery, a friend of mine, Mike Kennan, felt rather strongly that light bulbs were a poor choice for a test load. He thought that this effect should be used to push his lazy butt around. So he built the world's first real Tesla Roadster. This little cart here, notice that it has no batteries on board. All of the power for driving it comes from this aerial up above, which is essentially a disc made out of welding rods. It collects the electric field lines from the ambient fields of the coil and sends that power down here to a little small Tesla coil that operates in reverse and steps down the voltage. That voltage then goes over here. We have a 90-volt DC electric motor feeding a gearbox that drives the cart around. Here's a short video clip of the Tesla Roadster in action at a Maker Faire a while back. You'll note that Mike is wearing some heavy gloves, big welding gloves. He kept complaining about getting shocked from the steering grips. So it's too bad we didn't collect the energy that was falling on him as well. And when the cart starts moving, you can see some lively sparking from the ground underneath. That's a chain that it's dragging to form the earth connection. not sure the crowd really understood from my description that this was being powered wirelessly. At a maker faire, you just assume everything has lithium-ion batteries in it. But this is the world's first wirelessly powered vehicle that I know of that can carry a person. So the question remains, would Tesla's Wardenclyffe tower have worked? For near-field power applications, absolutely. Given that our accidental rig could deliver over a horsepower, a machine the size of Wardenclyffe would easily run 30 horsepower loads in the immediate area. Tesla could have even hosted wireless drag races at Wardenclyffe over 100 years ago. How about far-field coupling to the ionosphere and beyond? My intuition still says no, but you could say that I've already been burned once by my intuition on the subject. More recently, several groups have tried to answer this question with computer simulations, but it turns out to be a huge problem. A simulation of this size, including the ionosphere and the towers, presents over 10 billion degrees of freedom. And so far, nobody's been able to pony up the thousands of server blades that you would need to attack this problem with computers. I'm convinced that the fastest way to get answers to this problem is the empirical method. Simply build a resonator big enough to test the idea. Okay, back to you, Mark.
Thanks a lot, Greg. I appreciate it. I see some comments from the audience. Would love to enable them to ask questions. My first is that you have another presentation after this one to go over some of the technology that you've been researching, I believe, correct? So I'll limit the questions in between.
Okay.
But to that end, what we were seeing, the Roadster that you had powered can you ever see something like that being used outside of like the R&D spot, but maybe even from a commercial perspective, where we're wirelessly powering cars on our freeways?
Oh, certainly, that's one possibility. Another one would be, imagine a factory full of robots that don't need batteries and don't need to connect for recharging, but can just run continuously powered without wires.
Right.
That aren't purely vehicles.
Sure. Are you aware of anybody working on those kinds of applications yet, or no?
No, I think Mitsubishi was interested at one point, but they never went through it. It could be potentially a hostile area for people. But
Okay.
yeah, I haven't seen much work in that regard.
Right. Just
I would expect there at least be examples of wirelessly powered vehicles by now.
So I just, I want to make a quick announcement to our audience. I know some folks experience technical difficulties. Zoom, we do have a premium account. However, Zoom had noticed us that because of the volume on their entire system, they're having bandwidth issues. So I apologize for any inconvenience. I did see one of the questions in the chat. Are you currently working on building a 120-foot Tesla coil? That came from Dave Madigan.
Oh, well, I would love to build a 120-foot Tesla coil. In my next set of slides, I'll talk about that in greater detail. That's about the minimum size that you need to explore some of the interesting physics that happens in storm clouds. Of course, I can't afford to do that. I'm trying to find people that are interested.
Well, we'll leave it for the next presentation. I forgot that that's part of that. We have a question from Stanislav. Is the wireless frequency impacting electronics controlling the car?
No, the wireless frequency is driving the car, and the car itself really doesn't have much electronics in it. It's just got a reverse Tesla coil, some fast rectifiers, and a filter, and nothing else in there. Although if you wanted to add electronics, it's relatively easy to shield. Just a layer of foil is sufficient.
So one of the questions, people often ask me is the Tesla coils that, not only your tremendously huge Tesla coils, but the smaller Tesla coils that people sometimes see on display and being used is, I know that the original tower obviously was supposed to be a radio transmitter, but is it also a Tesla coil basically? Or what was being, do you know anything about the radio transmission that was part of it? And is it a dual purpose kind of tower?
Well, Tesla's design for Wardenclyffe, he was very adamant to say it wasn't a radio transmitter. It didn't use the Hertzian principles that Marconi and other people went on to refine. He didn't go into a lot of detail. He kept a lot of things close to his chest. But from some of his diagrams, it appeared that he wanted to capacitively couple to the upper atmosphere and just send power through capacitive coupling to a conductor and then back down again to other towers. And that's more a near field effect, whereas radio transmission is a far field effect.
Got it. One of the questions from the crowd, they must have saw one of your demonstrations in Little Rock. They were wondering what improvements you might have made since that demonstration to your coil.
Oh, several, mostly practical improvements. At the end of the Little Rock show, where we, my MO is typically to keep turning the thing up after the show is over into kind of an encore phase, and also to learn a little bit more about the machine, is I just keep turning it up until something fails. And in Little Rock, it failed in a really interesting and spectacular way. One of the arcs came down, struck the ground, traveled across, and then arced to the battery bank that we used to power it. And that's what knocked it out of the show. And since then, we've provided active shielding for the battery banks and some recovery circuits inside the primary drive system. At this point right now, the coil pretty much works well, and we're just refining robustness factors like that.
All right, if nobody has any other questions on Craig's demonstration or presentation on Tesla himself, Greg, maybe you can go a little bit more into the research of lightning on demand and the mysteries of lightning.
Okay. Lightning is an odd beast. As I mentioned earlier, we understand some things about it, but not the important parts. Lightning kind of starts off with a creation event in the clouds. And then if you slow it down about 7,000 times, like we're doing here, you can see that from the creation point up here, a whole bunch of tendrils come out. And these tendrils are called stepped leaders. They're not very high current. They're usually just hundreds of amps. And they can travel about 100 meters every 50 microseconds. And then what happens is these stepped leaders follow lines of electric field below the cloud until one of them eventually touches the ground. And when it does, that short circuits the cloud to ground, and you get the what's called the return strike, which can be anywhere from 20,000 to 130,000 amps. And that's the strike that you see with your eye when a lightning strike occurs. The main strike and the leaders are fairly well understood. The part that's not understood is up here in the cloud where the lightning originates. It's a mystery still because it takes about 2,000 kilovolts per meter to break down air and start an arc discharge. Yet if you measure the fields inside a storm cloud, you only see 50 to 200 kV per meter, a 10th to a 20th of what you need. So how does it get around this and start arc discharges? The answer is we don't know. And for me, it's really odd to think that here in the 21st century, we don't know what this trick is. It seems like it'd be an amazing trick to understand and use for other things. However, a couple of Russian physicists, Gorovik and Zybin, came up with a novel theory to explain how it performs this trick using a bit of relativity. They gave their theory a great name to boot. They call it relativistic runaway breakdown. Now, in their theory, they start with an electric field in the middle of a cloud. This field doesn't have to be strong enough to break down air. It only has to be strong enough to accelerate free electrons. A cosmic ray enters this electric field and strikes an atom. Under the right conditions, this cosmic ray can knock off electrons from the atom at relativistic speeds. Now, a curious property of relativistic electrons is that they're moving so fast that due to their warped space-time, their size shrinks, which significantly reduces their friction in air. This allows them to accelerate to near the speed of light until they eventually do hit other atoms, and they can knock off more relativistic electrons at that point. This can start a chain reaction, which would precipitate into a classical arc discharge. Sorry. This theory in the late 1990s started gaining some popularity, and a number of researchers went out to try to see if they could detect the telltale gamma rays and possibly positrons that the theory predicted. And they looked for about 10 years and never found any gamma rays. And it turns out they were looking in the wrong direction. I have a short video here that from NASA that describes an accidental discovery made by NASA's Fermi Gamma Ray Telescope a little while back. Let me play the video for you.
At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.
So thunderstorms really do produce both gamma rays and antimatter. But the Fermi discovery has raised more questions than answers. Why aren't there, why are the gamma rays head upwards? And more importantly, are there ways that we could hack this fantastic game mechanism? Wouldn't it be useful, for instance, if we had the ability to turn off lightning over populated areas? The actual workings of this game mechanism have eluded us for decades, since floating instruments at the exact right place and right time inside a storm cloud is practically impossible. But is there a way that we could recreate this effect on the ground, where we could see what's happening in detail? And that's basically what I've been trying to do with my work at Lightning on Demand. The theory predicts that all we need to trigger a relativistic runaway breakdown is to generate a critical field that's 200 kV per meter and about 80 meters total, about 80 meters in total length. Fortunately, 200 kV per meter times 80 meters is only about 16 million volts end to end. I've done a bit of research on ways to generate a field of this size, and I'm happy to report that it's not completely crazy to do. The best way I've found so far is to produce 2 identical Tesla towers. Other machines like Marx generators, and Van de Graaff machines, and impulse generators are much heavier, more complex, and quite expensive. Splitting the problem into 2 8 million volt towers, like shown here, is also makes things a lot easier, practically speaking. Now, modern structural plastics can support about 7,000 volts per inch outdoors, and that's if they're well cared for. So each of these towers needs to be about 120 feet tall to support this much voltage. It's spaced about 317 feet apart to get the 80 meters of field that we need. Here's a few interesting numbers that fall out of the full-scale machine design. The design target for the output voltage is about 20% higher than the required 16 million volts that we need, because historically, large-scale machines always run into some intriguing corner of parameter space that's just out of reach. The primary drive system for this tower, or each of the towers, is split up into 12 stations in order to use commercially available silicon. Each station uses IGBTs. They use the largest 6500 volt transistors that are available. Now, we're used to processors containing millions of transistors, but a single one of these transistors is about the size of a phone book. These type of transistors are commercially used right now to power high-speed electric trains. Now you might look at these numbers and think this is kind of a crazy thing to do. But building something at a scale far beyond what's done before is risky, of course, but it has happened and it has to happen. I'd like to show you a clip about two unusual coils that I've built in the past. I didn't plan on building either of these. Both of these projects just kind of fell from the sky. But at the time, both ended up being the largest coils in the world when they were built.
The first of these two Tesla coil projects was born from a salvage yard in 1990. I stumbled across a pile of capacitors, transformers, and bus bars that clearly wanted to become a Tesla coil. I brought the heap of parts over to Survival Research Laboratories, a machine performance group in San Francisco. SRL provided the machining and fabrication expertise, and in a few intense months, we had built the largest operating Tesla coil in the world, capable of throwing 25-foot discharges. This coil found its way into many SRL performances, where I learned a lot about the fine art of building cutting-edge machines from salvaged and donated materials. The second large coil project was as unexpected as the first. A kinetic sculpture artist by the name of Eric Orr asked if I could make his new sculpture produce 50-foot electrical discharges into the air. I of course quit my day job and immediately started on the design. The result was a 4-story high sculpture concealing a 130,000-watt Tesla coil, the largest of its kind in the world. At full power, the arc discharges reach up to 50 feet from the top electrode. The unusual scale of electrum allows a person to actually stand inside the electrode at full power. Aside from being incredibly fun, riding the electrode at millions of volts provided a rare educational experience.
Now, electrum was a pretty big coil, but its design wouldn't scale to 12 stories very well, being made out of solid fiberglass and stainless steel. To show that a 121-foot tall Tesla coil isn't completely crazy, I thought at least I should demonstrate a 1/3 scale model of one tower. So for the last 5 years, I've been building this 40-foot tall, fully functional scale prototype. Now, even the scaled prototype is more than twice as large as electrum, which used to be the largest operating Tesla coil ever built. And since I had to build this 1/3 scale prototype without any funding, this prototype also necessarily explores how to build a high voltage structure in the cheapest way possible. To minimize cost, this coil features a fully collapsible tower design. This tower you see here is inflatable, and the primary is broken into segments here, which collapse. So you can see they're slightly conic and they'll stack up like cups when it collapses. The top electrode is also inflatable, measures about 25 feet in diameter, and the radius is set to where it can hold about 3 million volts. Down here at the bottom, there is a small inverted cone. That's the primary winding. And the drivers for the primary sit on either side here. This is the coil in operation, our first tuning test that we did. Over here, I set up a 22-foot high tower to use as a ranging test. And for our first test, the coil didn't quite make it to 3 million volts. We got to 2.8 million volts and 160 amperes of displacement current to free space. It turns out there was a problem with unbalanced parasitic inductance down here in the primary winding, which we worked on later. So the coil seems to work okay. There's no problems scaling to 40 feet. In fact, the scaling laws look pretty rather favorable towards going towards 120 feet. A little bit after we finished this coil and got it running, I got a call from the Tesla Science Center asking if there was some coil that we could bring out to celebrate Tesla's birthday. So I figured since this thing is fully retractable and collapsible, I would just pack this thing up and drive it out 3,000 miles to show up at Tesla's birthday party with this coil. I think they were kind of surprised when I showed up with this, but we set it up on Tesla's old tower foundation. And my main concern after getting there was, what am I going to do for an earth ground? I was hoping that Tesla's original earth ground system, which consisted of a bunch of tunnels and such, was still accessible, but of course, you know, the towers of, or the tunnels have all been filled in, or at least the access has been. So what to do for a ground? In desperation, I took some measurements of the old granite blocks that were used to support the tower. There were these 2.5-inch diameter steel spuds that used to stick up, that were used, they were all thread, and they were used to hold the tower down. I attached some wires to them and made some measurements just to see if they have any ground connection at all. Because, you know, Tesla was kind of a stickler for details. And I would think that he would want any structural steel to have a dedicated connection to Earth. So maybe these under the ground had some connection to whatever array that he had intended for the coil. And it turns out these spuds going into the granite are amazingly good ground connections, way more than you would expect for a piece of metal just stuck into granite. When you attach them all together, it measures less than a half ohm to Earth. And to give you an idea of how good of a connection that is, if you take an 8-foot copper rod that's used for grounding buildings and you drive it into the ground there at Wardenclyffe, it measures 1,200 ohms, you know, over 1,000 times worse than these spuds. Makes sense since all of Long Island is essentially a big sandbar. So we ran a wire to each one of these spuds sticking out of the granite and used them as our earth connection. Here's a clip of the 40-foot tower running at Wardenclyffe using the old foundation as a ground. You'll see some flashing lights in the background. That's just some police out there on the highway. Apparently a big crowd gathered outside the gate. You'll also notice I keep turning off the coil every now and then. I'm trying to clear the ion cloud to keep the coil from hitting the trees.
Safety first.
The coil ran very well at Wardenclyffe. In fact, it ran better there than it does at the Alameda lab. I'm not sure if it's the really good ground connection or it just ambiance of the whole place. Maybe Tesla came back and put his finger on the primary drive. But It turns out it wasn't in danger of hitting the trees. It just looked like that from my point of view. And
Greg, before you move on, I just want to give the audience some context. What you were seeing there, I said that we had 1,400 people attend the birthday celebration, and then we had a nighttime event where we probably had another 500-600 people come back for that nighttime show. And when I got to get up to introduce Greg, we realized there's another 300 people outside of that fence. So you saw all those flashing lights. Part of that was crowd control. Part of that, there was a little fender bender because we had somebody rubbernecking and watching the coil go off. But all in all, it was a tremendous community event. But sorry, I just wanted people to understand the context of what they were seeing from the crowd perspective.
I was particularly excited that the ground system worked really well there. And, you know, like I was saying, Tesla kept a lot of details close to his chest. But after doing some research and talking with Douglas, that granite block that they use there, that's a particular species of granite called gneiss. And the variants from Germany turn out to be highly conductive because they're filled with potassium, sodium, and calcium. And I believe Tesla knew about this at the time and used those not only for the foundation anchor, but to provide the ground connection to the earth. And 115 years later, it still works great. And so hats off to Tesla for the weird little conductive granite trick.
So he knew what he was doing.
Yeah, he was full of surprises.
Greg, some of the crowd's asking, like, that was, you know, they saw that demonstration. That's amazing. What kind of decibel level? Do you have any idea of what we're dealing with for decibels there?
Well, from where I was at, and I was probably the closest one, I had hearing protection. It wasn't actually totally necessary, like somebody running a chainsaw nearby. And yeah, one more note on the grounding system. Tesla's original shop had a 200 kilowatt alternator, so presumably he could run his coil up to 200 kilowatts. The 40-foot coil can run up to 240 kilowatts. And in that last burst there, I was running around 210 kilowatts. So at Tesla's full power capacity, whatever ground system was there would have taken it.
So we have a couple of questions from the crowd. I don't know if I could ask you now before you proceed. One is, if you had the two coils, you know, a couple of 100 meters apart, why would the spark make it to the other coil as opposed to hit the ground? And is it really that you're sending sparks, or are you just sending an electrical charge, I guess, is the follow-up to that?
Oh, okay. Well, one reason is because the electric field lines tend to go horizontal. There are some local to the coil. But it's amazing how far they'll go horizontally between two coils. And in the experiment, I'm trying not to have any arcs at all. I'm trying to generate an electric field. However, if we do get a relativistic breakdown effect, that could precipitate into an arc that might launch 5 to 10 times further than a classical arc discharge would.
Got it. And before you move on, it was an earlier question, but when you're dealing with megavolts, how do you measure that? Is it a voltmeter or?
The easiest way to measure the voltage is you look at the current in the base of the secondary coil. And that current, through conservation of energy, translates into the voltage at the top. You take the energy in the inductance, which is 1/2 the inductance times the current squared, and you convert that to energy on the capacitance at the top, which is 1/2 times the capacitance times the voltage squared. There's a little bit of a loss, but you can set a maximum limit for what the voltage would have been.
And then I'll do one final question, then I'll let you move on. The role of the aquifer that's under Wardenclyffe and the salinity of the water, do you think that has any effect on the aux and in controlling the aux?
The aquifer definitely contributes to the ground conductance,
Okay.
and to that degree, it helps. But once you get to the surface, it doesn't see the aquifer, it just sees the surface of the soil in terms of shaping the electric field. The field itself doesn't penetrate too far into the earth.
Okay. There's so many great questions, so I'm going to let you move on, and then I'll see if I can come back to them.
Okay. Well, the third scale coil works. It looks like it'll scale well to 120 feet. And but a third scale tower is all I can manage on my own. And that took 5 years of scripting and saving and cost cutting. To build the full 120-foot twin towers, I'm going to need real help, of course. Try to find somebody who finds this level of research interesting and who's able to help funding it. And with luck, we'll bring the coil back to Wardenclyffe for Tesla's birthday this next year. The scheduling of that will all depend on how this pandemic plays out, but here's hoping we can bring it back.
That's right.
And if you'd like to read more about the scientific motivations behind my work, please check out the research page at LOD.org.
Thank you so much, Greg. So some of the questions were, would you consider using silicon carbide devices instead of silicon?
Oh, I'd love to use silicon carbide, and there's been a lot of progress lately on silicon carbide. I need to get the voltage up as high as possible, though. Regular silicon has 6,500 volt devices available, with work on 17,000 volt silicon for regular silicon, that is. Silicon carbide, you can get 1,700 volts now. 3,300 volts is in the works. And yeah, I have high hopes for silicon carbide. Thing of age here.
A second part of that question, but it's been asked a couple of times from some of our audience. What kind of funding is necessary to move forward to build the 120-foot coil or the two 120-foot towers or 121-foot towers?
Well, that number has come down a lot since we've built this prototype coil, going from solid 12-story towers, which require dedicated real estate and such, to an inflatable structure has really cut the price. And I think now that 120-foot towers could probably be built for less than $2 million each.
Okay. So I'm seeing people give a lot of suggestions on funding. I can say to our crowd, it's a goal of the Tesla Science Center after we launch, after we open the historic lab to the public, which is our #1 goal, and obviously offering great virtual programming like this. But once we're operational, there's a 3-dimensional plan for the Tesla Science Center. It's the museum and the historic lab building. It's a science center that highlights research like this and some of the most cutting edge exhibits. And the third piece will be an accelerator, a business accelerator, or a science accelerator, where if we find a project like this, we can come back to our crowd and we can partner with an innovator like Greg or a company that has a product and find ways to help accelerate that research or that product. So I'm assuming that Greg is going to be able to pull off the funding before we have an opportunity to help him. But hopefully we can help him a lot faster as our project continues to progress. Little update on that. Our plan was before COVID-19 to open the visitor center by the end of this year. We have permits in place to start some of the construction on site. We actually were working on the lab building for about 3 weeks, restoring the chimney and cupola. And then obviously because of social distancing restrictions, everything's been put on hold for a bit. But once we come out of this, we'll hit the ground running again. And in the meantime, it's good to have dialogue with our crowd and with friends of ours like Greg Leyh. Looking at some of the other questions, you're shooting off, basically lightning bolts. I think I might have asked this before. Is the use of the Tesla coil, if it was ever to be used for practical purposes, obviously we're not going to have lightning shooting around us, but it'll be an electromagnetic field. Are there any studies out there on the effect of that kind of field on organic matter or the human body or a human cell? Is that a cause for concern if we ever, go beyond researching this and trying to create products out of this kind of wireless charging or anything to that effect?
Well, electric fields and a Tesla coil produces predominantly electric fields. It produces magnetic fields, but they're not as prevalent and don't carry as far as the electric fields do. The electric fields, when they hit your skin, since you're reasonably conductive, they don't go very far. They may go in a millimeter or so, and then they just turn into circulating currents in your skin or muscle layer. Your muscles are very conductive and they kind of act as a ground plane in your body. So the electric fields themselves don't really affect living matter, since living matter is so conductive.
Okay. So it'd be more radio waves or microwaves. Now I know microwaves are ionizing, and a lot of the other waves that we have around us, like the old UHF or even some of the wireless communications from cellular, they're non-ionizing. But this isn't even a radiation. This is the electromagnetic field is a different wavelength altogether.
That's right. This isn't radiation. It's just near field.
Okay. In terms
you can feel it.
Yeah.
When the coil's on, and if you're when you're close enough, you can actually feel the coil running. And if you hold up a fluorescent tube, it'll light up in your hands.
Right.
But other than that innervation, the electric field doesn't penetrate very far.
If you're able to prove what is the terminology again? The relativistic
runaway breakdown.
Runaway breakdown. If you find that and you prove it, is there an application that you could think of from that? What does that mean once that's proven?
Well, a theory can only be proven false. However, something like relativistic runaway breakdown, if we discover what's called the gain mechanism behind it, it's got this incredible gain mechanism. It's usually pretty easy to disrupt or stop a gain mechanism. And out of this might come a practical application such as being able to redirect lightning or just stop lightning altogether over certain areas, like over populated areas or over power plants. And if, once we know the gain mechanism, what will precipitate out of that is an idea of some device on the ground that could affect it and allow us to control where lightning hits.
Okay. So this is a higher tech type of lightning rod to protect assets potentially?
Yes. Whereas a lightning rod does two things. First, it tries to shield the building by spewing off ions and kind of forming an ion cloud that makes the building look less sharp. And then when that fails, it provides a connection point for the lightning. And then there's a big thick cable that tries to route it around the building to ground. Whereas what we would do here is somehow affect a thunderstorm that's above a populated area to where it can't start lightning in the first place.
I'm hearing from Greg that in terms of some of the studies, Witricity, which is a company I keep hearing about that does induction charging for things like cell phone, and they're sending wireless energy to components in your room. They've done some studies on the safety of that. So if we find those studies, we'll share that with the crowd. I have a question from.
Oh, now I should point out that Witricity is a completely different thing. There, they're using magnetic fields to power things remotely. They'll have a big coil loop. The problem with that is it doesn't reach very far. It reaches about 1 coil diameter. You wouldn't be able to use Witricity to drive around a small electric vehicle like we did in the video.
Okay. The other question that I saw, and I'm sorry I lost track of it, is a Tesla coil safe for people to view it if they have a medical implant, like a pacemaker?
Well, I can't say for certain because there's different types of implants and some might be more susceptible to others. I do know that of all the signs that are put on microwave ovens and such about pacemakers, there hasn't been an actual incident of a microwave oven or a transformer affecting somebody's pacemaker. It's just kind of a precautionary measure. And we had somebody at one of our shows with a pacemaker. They stood back a ways, but they didn't have any problem.
Right.
So
just
I can't say for certain.
Everybody in our crowd, we are not taking a position on that question, and we are not giving any medical advice here. So always proceed with caution.
That's right. It's up to the person viewing.
So Greg, in some of the conversations that you and I have had over the past year or two, you were able to basically explain to me Tesla's invention pathway, where, and I think it was you that told me this, but each invention seemed to build upon the other and taken as a slice out of his invention, the annals of his invention, that many of them had a practical use, but he was pursuing something larger. So he wasn't doing the milestone commercialization. So he did X-rays before Rankin, but he didn't look to commercialize X-ray. He just wanted to understand X-ray tubes and to be able to direct energy, from what I understand. And then that all built upon each other. Can you speak to that again?
Well, his work with X-rays, like you say, was largely born out of curiosity. You can imagine, being 1888, and there's these rays coming out of there that heat your hand and can actually look through your hand and expose photographic plates. He did combine that knowledge with a few other things, though. When I read some of his letters at the Tesla Museum in Belgrade, he was describing what was later termed his death ray. And I had always wondered about how this death ray would work. How could you point it at an airplane and direct energy at the airplane to possibly knock it out of the sky? What he wanted to do was to take a suitably large tower, maybe like Wardenclyffe, and on top, he would have a quartz tube with tungsten caps at the ends that he would use as a big X-ray tube running off the voltage from the tower. The tube would then produce an X-ray beam, which he knew was ionizing radiation. And it would essentially produce an ionized stream towards the thing he was pointing it at. And then the hope was that the voltage from the tower would jump onto the ionized stream and head out to the target in question. Whether or not that was practical or if he could make a tight enough X-ray beam was a detail he never had explored. He just came up with the idea.
Okay, appreciate that. In terms of, I'm going to ask you to speculate a little bit. Knowing Tesla's methodology, knowing what his research interests were, what do you think he'd be most impressed with today?
What would Tesla be impressed with today? Definitely the space program, how pervasive the internet is and how much bandwidth is available now. That impresses people who predicted, 20 years ago that bandwidth would be the limit, and that we would literally have to send DVDs to the local 7-Eleven or newspaper vendor, and that's how you would get the internet. That prediction wasn't that long ago. Those two things would definitely impress Tesla. Nuclear power, that would impress him as well, that we finally cracked the atom and got at the strong and weak nuclear forces there. Mass production, I think he would have been impressed with too.
Okay. Now looking at some of the inventors today, do you see who are the Teslas of today in your mind?
Oh, geez, the Teslas of today. It's no longer one particular person. It's usually small groups now that are doing that.
Okay.
I'm a big fan of SpaceX. SpaceX has done some cool stuff. Landing the rockets back upright to reuse them, that was just incredible.
Yeah.
The electronics world, electronic engineers nowadays don't use the electron as a carrier of energy so much as a carrier of information. So our focus has headed off in different directions. There are a few people out there, though, that have been refining lithium-ion batteries. There's a fellow named Luke Workman who's done a lot of work there, and he's kind of a Tesla of lithium-ion batteries.
Do you see anybody out there that's less concerned with the money aspect of invention, but in trying to improve humanity through innovation? Is the gentleman that you mentioned doing the lithium-ion batteries,
He's actually a good example of that. He would build lithium-ion batteries from scratch just because he thought it was fun. As a consequence, he knows them very well, and the money concern is secondary or tertiary to him.
Appreciate that. And then, so from your perspective, I know you spoke about the coils. What do you find most impressive in Tesla's work?
The thing that's most impressive about Tesla is how he could come up with some of this stuff just with a blank sheet of paper. In modern day, it doesn't seem like so much, but to come up with ideas like the polyphase induction motor, when he had professors telling him that it was similar to perpetual motion machine, that you could generate a rotating field that could synchronize to a stator to a rotor and produce torque. That and the lighting tubes without wires, that's nothing short of being a magician back then. And then projecting some of that to ideas of what would happen in the future, such as having a little portable device that could pick up radio waves and transmit information instantly, even images. That was a cool one to foresee.
Yeah, I appreciate your time. Is there anything that I didn't ask you that you wish I had, or any closing remarks before I close it out with the audience?
Oh, what should you have asked? Oh, I wonder if we'll ever follow up on some of his ideas. In particular, trying to see if we can find usable resonant nodes in the ionosphere. And if you do some quick computer simulations, it shows that the ionosphere, just due to its size, can have Qs of like 800, which is amazing. But to couple to it is the challenge. And whether we'll find that kind of weird, esoteric pursuit interesting enough to throw money at it that's what I wonder if that'll happen.
Well, hopefully we can find out together. Want to thank you for your time. For our audience, I know there are a number of questions we didn't get to. My staff and I will go through the chat. We're going to download this chat. We're going to database these questions. We're going to make sure that they get answered. And we will email the participants the questions and answers. So your question will get answered. Want to remind everybody to keep tuning in. We will have another program coming up for Tesla Unwired, and this will be an ongoing series. We recently launched the Tesla Lego Challenge. For those of you who have not heard it, we are challenging both children under 12, children between 12 and 17, and adults. It's 3 categories. Using Legos, recreate the Tesla lab at Wardenclyffe. You can upload your design after it's built to our website. We are going to allow a worldwide vote for winners. There is prize money. It's $1,000 for the adult winner and $500 for each category for the children. We'd like to get that message out there while people are home social distancing. This is something that families can work on together. And it helps raise awareness for this project, taking Tesla's lab and opening it to the public. So please help us share that message. Continue to tune in. Thank you for your time. And thank you, Greg. Really much appreciated. I hope we return to whatever our new normal is going to be, and we can get the Coil back to Wardenclyffe for some sort of a celebration this year.
Yeah, thanks for having me.
Goodbye, everybody. Look forward to seeing you next time. Stay safe.
Thank you, Greg. Really appreciate it.
Yeah. Are we still on the air? I see there's about 57 people.
We are. Feel free to chat. Feel free to chat.
You're on.
Just remember that ozone kills viruses. Generate lots of ozone.
I just, somebody was saying that in the chat, and we should be all firing off our Tesla coils.
Yeah, helping to replenish the ozone layer.
You just answered a question of mine.
What is it? Yeah.
I have a I'm gonna call these guys. I want to know more about that. I have an ozone cleaner, like for my CPAP mask. And, it's like a chamber. You put your mask in there, and instead of washing it every day and all that stuff, you put it in this ozone chamber, and the ozone runs through your machine and your mask and everything, and it kills bacteria and all that stuff.
How would it kill you?
So I put my, let me turn this off.
No. That is not happening. Nothing is going on here except excellence. Okay. Well, you let me know what you want to do, and I'll think about it. Okay. Well, thanks for coming.
Hey, is there anyone out there that could answer a question about ozone and killing viruses and bacteria?
The negotiating tactic?